Good afternoon to all of y'all. In this video, we wish to derive the volume flow rate of a viscous fluid through a thin capillary tube. It is also called as the Poiseuille's equation. Let us first see the basics of viscosity. Before we go to viscosity, supposing we had a cube which is fixed here, the cube which is fixed here, yes, and we apply a force F like that on it. So obviously uh, the surface on which the cube is fixed will exert a force like this. There will be a couple like this, and this cube which is there will get sheared. Yes, this cube gets sheared. That cube which is there becomes the square which is there becomes a rhombus. So this is what the cube becomes a rhombus. So if this height is say some y, and if this is delta x, then this angle is called as the shear angle phi, and the shear angle phi is given by delta x by y. This is called as the shear strain. The shear strain, yes. And if this is the area is A, the shear stress is F divided by the area. Now, this was a solid block. Liquids and fluids also get sheared. Let us take a fixed surface and let us say there is a thin layer of oil, and on that we have a glass plate. This is a glass plate which is now being moved with a constant velocity v. Now it is being moved with a constant velocity v. The oil layer is also going to move. The oil in contact with the glass surface will move with the same velocity v. The oil layer which is at the bottom in contact with the fixed surface will be at rest. So therefore, you find that there is a velocity gradient. Let us say the thickness of the oil is z. So this is z. Here the velocity is 0. The velocity gradually decreases and becomes 0 at the bottom. We say there is a velocity gradient. Yes. If you choose this as say one axis y and this as say some axis z, then the velocity would vary like this from v to 0. This, let us say, we choose as the origin for a y. Okay? So this is how the oil, the liquid which is there will get sheared. Let us see what is the shear strain. Yes, let us see what is the shear strain. The shear strain is the liquid, the oil in contact with the glass will move by a distance v into t in a time t, and the bottom portion is not moved at all. So the shear strain would be was delta x by y, that is v into t, which is delta x, by y, which is z here. That is the shear strain. The strain rate is the shear per unit time. That is nothing but v into t by z by t cancels, is v by z. So the strain rate is v by z. Yes. Now you must note that the liquid at the top is moving because of a viscous force Fv. Now by Newton's third law, there will be a viscous force Fv in the opposite direction on the glass plate. So in order to move this glass plate at a constant speed, you will have to apply a force F, which is equal to the viscous force. Yes. Now we define the coefficient of viscosity. The coefficient of viscosity as the shear, viscous shear, as the viscous shear divided by the strain rate. Strain rate. The symbol used is eta. So this would be Fv by the area. A is the area of the glass plate in contact with the oil. So Fv by the area. Yes, this is the area we are talking about. This is the area A. Okay. By the strain rate, which is V by Z. That is how we define the coefficient of viscosity. Now you see the slope of this line is minus V by Z. Yes, if you visualize it like this, the origin here, y-axis and the z-axis like this, the slope of this would be V by Z. So we can, the slope of this will be minus V by Z. Yes, slope is minus V by Z. So V by Z can be written as Fv by A by negative of the slope. Now, if the velocity versus the Z graph, the depth from the surface graph is a straight line, we call it as a Newtonian fluid. But it's possible that it will be a curve, V versus Z. V versus Z is a curve. Then we will have to talk about the slope is a variable. So the slope will be given by dV by dz. Instead of V by Z, the slope will be dV by dz. So then the coefficient of viscosity can be written as Fv by A minus dV by dz. Yes? That is how we define the coefficient of viscosity. Now let us take a thin capillary tube and let a viscous fluid flow through it. Yes, let us take a capillary tube, and this is the axis of the capillary tube. The radius of the tube is R. Okay, and there is a fluid, viscous fluid flowing through this. Now the velocity of the fluid in contact with the inner curved surface of the capillary tube is 0. The velocity will be 0 here. Yes, the velocity is 0 throughout, and the velocity is maximum at the center. Yes, so there is a velocity gradient from the center to the wall. Okay, there is a velocity gradient from the center to the wall, and there is also what is known as a circular symmetry or cylindrical symmetry. That is, if we choose a cylinder of radius x, the velocity here would be v throughout. V is a function of x. The velocity v would be a function of x, and it is going to be the same all along the periphery of the cylinder of radius x. Now, if you want the velocity gradient, if you take another layer of the fluid with a distance of thickness dx, the velocity gradient would be dv by dx. Velocity gradient is going to be dv by dx. So now let us see how we can define this coefficient of viscosity. Now the liquid is flowing this way. Okay, so let us now consider the cylinder of length L and radius x. A cylinder of length L and radius x. On this cylinder, there will be a viscous force. The liquid is moving towards the right, so the viscous force Fv will act throughout the periphery tangential to the curved surface. Remember, the viscous force is like a frictional force. The slipping is towards the right, so the friction opposes slipping. In the same way, viscous force also opposes slipping, so the viscous force is towards the left. So now we are assuming that the whole liquid which is here is in a steady state, and it is a steady flow or a laminar flow. So the net force on this cylindrical liquid would be 0. So obviously the pressure here is P1 and the pressure here is P2. We can say the net force on this cylindrical liquid which is flowing towards the right should be 0, and this P1 should be greater than P2. So P1 minus P2, that is the pressure difference on either side of this imaginary cylinder that we are considering, that into the area. The area is pi x squared. This will be equal to the viscous force. This will be equal to the viscous force. The net force on this should be 0. We are assuming a steady state condition, a steady flow in which the velocity is constant. Okay. So we can now define the coefficient of viscosity as Fv by A by minus dV by dx. Fv is P1 minus P2, is called as delta P into pi x squared, that is Fv, divided by the area. For the area, the viscous force is acting along the curved surface area of the imaginary cylinder. Therefore, the area that you have to take is the curved surface area of the cylinder, that is 2 pi x into L divided by minus dV by dx. Okay. So we can get what is V from this as a function of x. We will get n eta minus n dV is equal to 1 pi cancels here, 1 x cancels here. You will have delta P by P, and you will have x dx by 2. X dx by 2 and delta P by L n dV. So you let us integrate this. We will integrate this from x to r. We will put the limit as x to r because we know the velocity at x is v and we know the velocity at x equal to r is 0. So we will integrate this from x to r. At x the velocity is v, at r the velocity is 0. The fluid in contact with the capillary tube is at rest. So this will be minus eta v, limits v to 0, delta P by L into x squared by 2 into x squared by 2, 1 2 is already there, and 0 to r. So this is going to be eta v, eta minus eta 0 minus v is equal to delta p by 4l into, this is not 0 to r, this is x to r. This is from x to r. So this will be r squared minus x squared. So therefore you get v as delta p by 4l eta into r squared minus x squared. That is the velocity as a function of x. As you can see, it is dependent on x squared. So therefore this equation indicates that the velocity and x are related parabolically. It's a parabola. That is, if you draw the velocity profile, the velocity profile would be like this. It would be a parabola. It would be maximum at the along the axis and zero at the periphery. Yes, it's a parabola. So we have v as a function of x. Yeah. So in fact, when the liquid comes out of the tube, it will have a profile like this. The profile of the liquid coming out of the tube would be like this in the absence of gravity. Yes. So once we have got this, now we want the volume flow rate. We can easily find the volume flow rate. We know if there is a tube of area A and the velocity is v, then the volume flow rate is A into V. Area into V is the volume flow rate. Why is that? Because in a distance, in a time t, dt, yes, the liquid will move by a distance v dt. Therefore, the volume that has flown is A into v dt. We want the volume flow rate by dt, so that is AV. So the area into the velocity gives you the volume flow rate. Now, if you see this velocity, it's not constant, it is a function of x. Therefore, you will have to choose an infinitesimal area. So if you choose an infinitesimal area, the infinitesimal area should be dA into V. That is the volume, infinitesimal volume flow rate. That is dA, we will choose it as 2 pi x dx. That thin ring, along that thin ring of thickness dx and radius x. So 2 pi x dx into V. V would be delta p by 4l eta into r squared minus x squared. Yes, that will be the volume, infinitesimal volume flow rate. Integrate this, you will get the total volume flow rate. So you have 2 pi delta p by L is here. Yes, delta p by L is here, and you have got pi by 2. This is 2 pi by 2, and you have an eta. Let's leave that like that, and this would be r squared. We are integrating this r squared x minus x cube dx. Limit should be from 0 to capital R. X should vary from 0 to small r. Yes, that is the. So let's integrate this. So integrated that, you will get delta p by L into pi by 2 eta as it is here. This would be r squared into x squared by 2. Derivative of x dx is x squared by 2. This will be minus x4 by 4. Yes, limits from 0 to r. So this will be delta p by L into pi by 2. This is, once you put the limits, this will be r power 4 by 2 and r power 4 by 4. So this will be R power 4 by 4 eta. So if you further simplify this, you will have delta P by L into pi by 8 into R power 4 by eta. That is the volume flow rate, or the through of a viscous fluid through a thin capillary tube. That is also known as the Poiseuille's equation. Now this Poiseuille's equation can be compared with the Ohm's law. Very interesting. The Ohm's law says if you have a resistor and if the potential difference is V, if the current flowing is I, then V is equals to IR. V is the potential difference. I is the electric current through the resistor. This is the electrical resistance. The electrical resistance. The same thing we could do here. The volume flow rate is the fluid flow here. Fluid flow rate. This is the fluid flow rate. Here, delta P, the pressure difference, is the potential, is like the potential difference. So if you rearrange this, you have V into 8 eta L by pi r to the power of 4 equals delta V. This quantity is the fluid flow rate or the fluid current. You can call V, the volume flow rate is the fluid current. Don't confuse this V with this V. V here is the potential difference. Here this is the volume flow rate, which is the fluid current. We are calling it the fluid current. This delta P is the pressure difference, and 8 eta L by pi r4 r to the power of 4 is called as the fluid resistance. Called as the fluid resistance. Yeah. So you can use all the formulae that you use for series resistances, parallel resistances, etc. for fluids as well. So if you have one capillary tube and another capillary tube like this, and the pressure difference you know is delta P. If you know the pressure difference as delta P, you can treat this as two fluid resistances in series. Yes, you can treat it as two fluid resistances in series. Okay, so this way, or if you had two tubes like this, and the pressure difference, pressure here is P1 and pressure here is P2, then you could treat this as two fluid resistances in parallel. These are two resistances in fluid resistances in parallel. So this way you can apply all the laws of electric current to this as well. Thank you.